We can hear
me?
you.
All right,
Yes.
we're good. Okay, so I'm going to pick up a little bit of the film that I sent you a link for, and then we'll take a look at bounding a differential equation. When you bound a differential equation, you limit the potential solutions that equation can have. And that has nothing to do with quantum mechanics. That's just the nature of all systems. Guitar strings, classical systems, doesn't matter. The reason quantum mechanics uses the term is because it tends to talk about the atom, and in the atom we're bound systems. We don't tend to talk a lot about free systems. But the language is universal, and it existed long before quantum mechanics ever came along. So that's our task today. We want to get through the Bohr atom if we can. We want to look maybe a little bit at Frankenhertz and do some problems. And other than that, we have one more thing before the first exam, and that's the wave nature of particles that we'll knock out probably on Monday. So after Monday, I will have enough material in there to actually give you an exam. So the thought is we'll continue moving forward. But a week from that time, we will have an exam, and I will arrange with y'all a time, probably sometime on Monday afternoon, since I believe that's our lab time, to have an exam. I will send an exam out to Prairie View, and Dr. Erickson will arrange a time for you guys to take your exam. It will be in class. It will be closed notes, closed books, open mind. Bring a pencil, bring a lot of paper, standard thing. Anything we've covered is fair game. You'll be able to finish the test in probably 30 minutes. I will give you at least 2 hours. So that if you're not as quick as I am, that's fine, but you've got to be able to derive. You've got to be able to answer conceptual questions. You've got to be able to solve problems. Same thing as usual. Not as big as in Physics 1 or 2 where I gave those big 5-hour exams, but still comprehensive. So make sure that you know the photon energy relationship. Make sure you know your statistics. Make sure that you know everything that we've covered in relativity. If it's in the notes, it's in the book, it's on the test. All right. With that being said, let's knock this thing out today. Looking at our desktop, let's deal with this film.
And in the spectrum of hydrogen. Soon, the Swedish master of the spectroscope, Johannes Rydberg, generalized Balmer's formula. In Rydberg's version, a series of lines was generated by each set of integers, m and n, and the quantity r, called the Rydberg constant, was measured with great precision. From that point onward, it was possible to predict new lines. But to understand the nature of the atom in a deeper sense would require someone to make a discovery along different lines. And that someone was Professor J.J. Thomson, a disciple of Maxwell in the theory of electromagnetism, and, in his own right, a man determined to look into the internal nature of the atom and to discover how it worked. Others would later turn the cathode ray tube into TV and computer screens. But more significant in the long run, Thomson's experiments showed that the rays emanating from a heated cathode in an evacuated glass tube were electrically charged particles. Most important, those rays could be deflected by electric and magnetic fields, and no matter what matter was in the tube, they were always the same charged particles. Thomson saw that all atoms contain the same working parts, or in his words, corpuscles, which would become known as electrons. With those parts in mind, he developed what was called the plum pudding model. And more than an intellectual snack, it was a substantial explanation for line spectra of the elements. In Professor Thomson's theory, each atom consists of a large sphere of positive electric charge, with just enough negative electrons inside to balance the total charge and to make it neutral. This seemed a sensible idea, but it would soon fail a crucial test.
And other new methods, we are able to break up atoms in a great variety of ways.
Baron Ernest Rutherford, Nobel laureate and peer of the realm. He'd come from New Zealand to study physics at Cambridge, and he'd had the opportunity to work there under Professor Thomson.
To a definite law like a radioactive element.
And by the time he spoke these words, he'd not only long since succeeded his mentor as director of the Cavendish Laboratory, Rutherford had become headmaster of the atom itself.
And has given us a much clearer understanding of the atom.
Even before Rutherford began his experiments, it had been discovered that atoms could split themselves naturally and emit alpha-ray radioactivity.
And the progress of our knowledge.
So when he and his associates passed alpha rays through thin metal foils, their experiments went precisely as everyone would have predicted.
Nuclear chemistry, which is concerned.
The rays seemed to slice through the metal as if it were a pudding, with very little resistance, and went straight along their course with hardly any deviation. But one fine day in scientific history, they noticed the unexpected. The most incredible event that has happened in my life, stated Rutherford after the fact. It was almost as incredible as if you fired a 15-inch shell at a piece of tissue paper and it came back and hit you. The incredible event was that rather than winging their way right through the foil, some of the alpha rays bounced back. Rutherford realized that contrary to Thomson's model, all the positive charge of the atom had to be concentrated within a tiny nucleus. That was because, with all the positive charge concentrated in a very small region, the electric force nearby would be large enough to repel, or at least deflect, an energetic alpha particle if one got close enough. In addition, if the nucleus had most of the mass of the atom, it could repel the occasional alpha particle without recoiling very much. These ideas led Rutherford in 1911 to propose a planetary model of the atom. According to Rutherford, the solar system and the invisible atom were almost mirror images of each other. Both obeyed nearly identical laws. In Rutherford's model, each atom had a heavy nucleus that was positively charged. His nucleus was surrounded by light negatively charged electrons that orbited like planets around the sun. But while the planets were bound together by the force of gravity, the atoms were held together by the force of electricity. Like a Greek goddess in the heavens, this was an idea of incredible beauty. And by the same token, it was too good to be true. For one reason, when electrons are accelerated, they radiate energy in the form of electromagnetic waves. But an electron in orbit would be constantly accelerating, always radiating energy. Going round and round, the electron would fall into smaller and smaller orbits, radiating not spectral lines, but a continuous rainbow of colors. And finally, necessarily, it would collapse into the nucleus. Dr. Rutherford had obeyed the laws of Newton and Maxwell. And those very laws were the downfall of his model of a planetary atom. What was needed?
All right, so going over those things that I covered last time, which I would expect you to be able to derive off your head, as well as be able to explain in words. Moving on. So we've got an atom that is not stable according to the Rutherford model, but we know that it has to produce spectral lines. And if it has to produce spectral lines, it has to be a bound system, because otherwise it would produce a continuum. So we're going to come back multiple times and deal with what's called the particle in a box, which we're going to have to eventually work from quantum mechanics with the wave functions. The particle in a box is exactly the same solution or the same mathematics as a wave on a string between two ends. And we'll find in the next lesson that an electron, proton, alpha particle, or even you have wave properties and have a wavelength. So, although I'm talking about a string in the notes here, I could be, and later on, be talking about an electron combined in a well, for instance, of a semiconductor device. if you have this type of system, and the system is unbounded, like the case of a free electron would be, then it can have any wavelength that it wants. It could have this wavelength, it could have this wavelength here, it could have that wavelength there. If you bind the system, however, so I've got two walls here, and I attach the string on one side and the other side. The fact that you have that system bound at those 2 points means that not all wavelengths are possible anymore. For instance, this wavelength is not possible. It doesn't meet the boundary conditions of the problem anymore. In German, there's a name for that. When you only have certain solutions, the solutions are called the eigenfunctions. And the values that determines which solutions are available are known as the eigenvalues. In this case, the eigenvalue is the wavelength. And the function, it looks like, is some sort of sine function. So each function, whether it be sine of a particular one, has a value associated with it. The same thing is true in quantum mechanics, we'll find out. For each energy level, there will be an eigenvalue, for instance, its energy. There will also be a function called the wave function associated with it. And that wave function contains information. And we're going to have to figure out how to find that wave function by solving a differential equation known as the Schrodinger equation. So, big things. A, they had to be bound. So you have to figure out how the electron is bound. That binding influences the frequency and wavelengths of electromagnetic radiation. And therefore, through Einstein, it affects the energies. The emission and the absorption spectrum of each atom are unique. They're like fingerprints. Spectroscopy says that if you know the spectra, if you look at the lines, then you know what elements are there. And furthermore, if you know their brightness, how intense they are, you can even determine how much is there. Today, that's actually used as an analytical technique. So, if I hit a material with a proton beam, for instance, and I look at the lines, the energy of the photons that come off, I can tell you whether it's made of copper or gold or vanadium or whatever. And I can even tell you how much it is without melting a sample and destroying it. This is the standard technique that's used for lots of things. Other thing inside of there, kind of finishing looking at what I wrote in your notes that you should have read. If you look at these waves on a string, or if you remember back in high school, since it's a required tax thing on the STAR exam, in fact, my daughter's doing that right now, then you'll know that the wavelengths here, in order to complete this, the longest wavelength is if it's this one where it makes half of a wavelength getting from one side to the other. So to complete that, this is kind of like the upside down sine wave here. To complete that, it would need another L. So that length is 2L. Every other wavelength will be shorter. For instance, this one is just the wavelength L. So the first one, the longest one, is 2L. The next one is 2L over 2, which happens to be equal to L. If you keep looking, the next one after that will be 2L over 3, and you can write that as 2L over some number n. In quantum mechanics, these n's are so-called quantum numbers. They're the L's and the n's and the such. When you talk about a 1s orbit, the 1 is one of those quantum numbers, those n's, and they come out of these eigenvalues. The L, you talk about 1s, we're going to give it a new number. It's not going to be s anymore. That L is what's going to be. It's going to be 0, 1, 2, 3, 4. So there will always be these numbers, and they determine these so-called eigenvalues. Other thing that we want in our system, besides just being bounded, it's going to have to obey Einstein's relation, because we're going to want it to produce photons where there's a relation between energy and wavelength. So Bohr knew some things. Now, where was Bohr? Bohr was a postdoc in Rutherford's lab. Rutherford hated theorists. Hated them. He liked experimentalists. He did not like theorists. In fact, he said he would have no theorists around in his lab. And it was often discussed, well, then why was he having Bohr? And he said, well, Bohr wasn't a theorist. He was a football player. Bohr was a world-class soccer player in his youth. In fact, his brother played on their World Cup team, and he was not as good as Bohr was. So because Rutherford loved soccer, he let Bohr hang around. All right? So Bohr knew a lot about what was going on. He knew what Rutherford was doing. He knew about spectral lines. He knew he had to bind the system. He knew he had to make sure it matched Einstein's equation. He had all that sort of information. Another thing he knew, you had emission and you had absorption. And if they were going to have the same lines, if the absorption lines were going to match the emission lines, then whatever energy was going on in the process had to be the same type. So he had this idea in mind. If you had the atom in some sort of energy state, let's say the electron here, and if the photon came in with a certain amount of energy, and it gave that energy to raise that electron up to here, then this energy gap here would be matched to the energy of that photon. And you would get absorption, and that's what would determine the absorption lines. He could make the absorption lines match the emission lines if the way in which you got emission was that between the same two difference in energy levels, this body somehow went down and gave up the same amount of energy. So by having a bound system where you went from one state to the other by absorbing energy and having exactly the same two states that you then went down to emit energy, he was guaranteed that his emission lines and his absorption lines would match. The only problem he had to do was to figure out how to predict these energy levels. So that's what he had. So here's how he's going to try to do that. His first thought is, well, he's got the Rutherford planetary model. And he knows in the planetary model that the energy of the electron has to be a combination of its kinetic and its potential. He also knows, as you should from Physics 1, that this is a rotational problem and you should be writing kinetic energy in terms of angular momentum because it's conserved for a central force problem. So he knew immediately to write that that was the angular momentum squared over 2 times the moment of inertia, and not to write it as 1/2 mv squared. Again, Physics 1, which you guys should know by now. He also knew a formula for the potential. He had a point charge in the center who had ZE, and he had an electron of charge E on the outside. So he knew, of course, that Q is Q times V. And he knew the potential here of the point charge. So putting those two together, he's able to replace U with KZE squared over R. He also knows something else. He decides to choose to make him in a circular orbit. And if you make something in a circular orbit, something else you should remember from Physics 1 in our work on gravitation, the potential energy is twice the kinetic for a circular orbit. So that means that this is twice of that. So if you have something like -1 and you add a positive 1/2, then you're going to get a -1/2. So he knew this. Again, you should be able to drive that. I would expect to be able to ask you that and have you drive that. That's Physics 1 by now. You should be able to drive it. So he had a formula for the energy. His problem was this. if r is the distance from the center of the proton, why can't it just take on any value of r at once? And if it can take on any value of r at once, it can have any energy E. And if it can have any energy E, then it can make transitions between any distance r, and you can get a continuous spectrum. What causes this thing to be discrete? The only way it can be is if the r's are discrete. In other words, the only way you can get discrete energy levels is if you have discrete orbits. So that's one problem. You're going to have to quantize the orbits. But why? Why should they be quantized? Another one is, what I haven't accounted for here is any energy losses. Word non-conservatives, radiation. According to classical physics, this thing should be losing energy by radiating, and that means this R should be going down as the energy goes. And I haven't done anything about that either. So, he has problems, but he also has some idea about where you're going to go with this. Now, Bohr decides that he has to make some suggestions, some postulates, some sort of assumptions if he's going to work this problem. And he's already made a couple by giving me this. So let's look at his assumptions. The first assumption, the assumption that Rutherford made and which worked for Rutherford scattering is, I'm going to assume the Coulomb force is involved. I'm going to assume that the nucleus is a point charge. If that worked for the scattering and it explained the nucleus, it makes sense that it should also be true for the electron who's sitting out there outside the proton in some orbit. So this is not very amazing or surprising that that assumption would be true. It's the second assumption that's weird. It's this assumption. And I'll try to explain to you where this comes from. He decides that he is going to quantize the angular momentum of the orbits. First, why work with angular momentum? It's a central force. It has no torque. If you have no torque in a problem in physics 1, you have conservation of angular momentum. Remind you that torque is R cross F. And that if F is the central force lying along R, then these two are parallel. And the sine of 0 or the sine of 180 is 0, so there is no torque. I further remind you that the sum of the torques is dl dt in physics 1. So if that's 0, that means you're taking the derivative of a quantity and getting 0. That thing that doesn't change is called a constant. So anytime you run a central force problem, I don't care what it is, whether it's gravity, electric field, whatever, then you're going to want to work with things that don't change rather than things that do change. And what doesn't change is angular momentum. We did a lot of that in physics 1. Okay? So it makes sense that he would have been looking at angular momentum because he knew it was a constant. The bigger question is, how did he know to make it in h bar? That is n times Planck's constant divided by 2 pi. He had two reasons to do that. One, the units of Planck's constants are the units of an angular momentum. So that's one reason. Second, integers make more sense to try than to try like half integers or something else. So where the hell did 2 pi come from? The 2 pi comes from classical physics that says that if you integrate a generalized coordinate times a generalized momentum, and you do that over a cycle or a closed path, this quantity is called an action. And it tends to be important in classical physics. And when you're in the junior level classes, you'll actually look at some different methods of writing mechanics rather than just Newton's laws. So he knew about this action. And he knew that a lot of classical physics problems are solved that way. Now, I said a momentum and a generalized coordinate. This momentum, if it's an angle, is an angular momentum. If it's a linear distance like x, it's a regular momentum. So you could think about p dx, or if you're doing a circle problem, it's L d theta. So he was looking at the angular momentum times d theta around a path. So here's a path. So he's taking a small d theta, and then he's taking the value of L, and he's multiplying it by d theta, and he's adding it up as he goes around that path to calculate the action. But I just said that L was constant. So L comes outside. So now I got L integral d theta. Now, what's the integral d theta over a closed circle?
2 pi.
Huh?
2 pi.
2 pi. So he gets L 2 pi. And so all he really did was he got L 2 pi and he said, hey, I know it's got to be an angular momentum. I know this has an angular momentum. Why don't we just put integer values of that? And try and see what works. Because I know actions are important. I know L is a constant, can come outside. I know this is L 2 pi. That has angular momentum. That has the units of angular momentum. And everything we've seen in quantum, photoelectric effect, Compton, Planck's work, H is always the thing that's driving it. So it makes sense it'll be here too. So he puts the H, he has the 2 pi, divides both sides by 2 pi, and he gets that. Now that doesn't mean it has to be right. That's just how he came up with it. It could be totally wrong. It could be that this needed to be H over 7. But that's what he tried and it worked. How do you know it worked? Because when he's done, he gets the spectral lines that have been measured. He's able to derive the equations of the spectroscopists with all their amazing precision and actually get the lines. So that's where he came up with this. Now it seems bizarre. It seems bizarre because it says if you do that, you can only have certain values of MVR. You can't just have any radius you want. And that doesn't seem to have any classical justification at all. Bohr knew this. He knew this didn't make sense. But he knew without doing it, he had no habits of explaining spectral lines. We'll come back and see why this is true. The Bohr model is wrong. The Bohr model is a lie. Quantum mechanics explains what goes on. So why do we keep teaching the Bohr model? Well, partly because it's part of the scaffolding. You need to understand the rest of the stuff. And second, it doesn't require advanced mathematics to do problems, and it gives the right energy levels. So it's incredibly useful for computational work. So the fact that it's wrong is not really relevant. It gets you what you want. Number 3. If you have these R's, fine, but then it's going to emit radiation and it should spiral in, and the R's should change, and you should violate this. How am I going to fix that? He said, just don't let it. So that sounds like cheating if there ever was one. All right? Basically, do not let it radiate. I'm using classical physics, oh, by the way, violate classical physics. That's what he did. Number 4. I violated classical physics. Now, by the way, I want to make sure I obey classical physics and conserve energy. 4 postulates. It's not such that the postulates are so bizarre. What's amazing is with 4 postulates and nothing else, I'm able to come up with basically the size of an atom. I'm able to come up with all the spectral lines. I'm able to explain all sorts of things that no one could explain before. And I only used 4 assumptions, 2 of which make total sense. Conserve energy, and the force between point charges is the Coulomb charge. It's amazing with so few ideas, you can explain so much. There has to be some truth in it, even if all the truth isn't there. Now, what Bohr will do that's more important than anything he did here is he will found a school and he will help shepherd all of the young physicists who will build the full quantum mechanics. This old quantum mechanics will go away and the new quantum mechanics will replace it, and Bohr will be the person who will be their leader. All right? But this is how he did his original work. From there's a bunch of things that I would expect that you should be able to work out for me. I would expect that you take those 4 topics, apply physics 1 and 2, and be able to derive me whatever the consequences of that theory says. So first of all, the size of an atom. Bohr sits down, he says, okay, there's CE for a particular atom, and I'm not going to make it hydrogen, I'm going to leave it more generalized. And I'll leave 1 electron out here. So I'm going to solve 1 electron atoms. And it turns out his theory still works pretty good for 1 electron atoms, not just hydrogen. Why did I say 1 electron atoms? Because I'm not going to consider any forces due to other electrons. So if you have helium plus, I would expect my spectral lines to look pretty good. If I had lithium double plus, I would expect my energy levels to look pretty good, and in fact they do. He puts the force in here, and he says, hey, it's going in a circle. If it's going in a circle in uniform circular motion, then that force has got to be the mass times the centripetal acceleration, physics 1. I can solve for R. So you can bring the mv squared, bring that R squared up here, bring that R there, bring that KEZ squared down here. This just seems kind of strange. I'm going to rewrite it in just a second. The KE squared can be replaced with what? Last class. 1.44 what? EV nanometers. So I've already got that. No need to be messing with that. You might think that you want to cancel one of those R's. Don't do it. I'm going to have a hard time. I don't know the speed of the electron. And I don't know the radius of the electron. And I don't want to put an equation that's got multiple things I don't know. I want to find and replace things in terms of L because I know Planck's constant, and I can then solve and eliminate things. So you don't want to remove this. You want to get MVR. All right? So it's easy to be chasing your tail in the algebra here if you're not thinking about the way Bohr did. He's wanted to find all sorts of L's if he can, because he can replace them with NH bar. So what he's going to do is he's going to multiply top and bottom by M. Now he's going to put a mass on the bottom, but he knows the mass of the electron. And on top he's going to put M squared, B squared, R squared. And he's going to group them. And he does that. And he gets R is MVR, all of that squared. Well, that's L. And then you're squaring it. And I have a formula for L as one of my assumptions, my postulates. I have KE squared, which is 1.44 EV nanometers. I have Z, which is atomic number, is known. I have the mass of the electron, which is known. Now, I don't tend to like to work in the mass of electrons, so what am I going to do? I'm going to multiply the top by C squared. I'm going to multiply the bottom by C squared. MC squared is the rest energy of the electron. L is NH bar. Plug all those guys in. I've got N squared on the top, a constant that determines the orbit. I've got the atomic number, which for hydrogen is 1. I've got my friend, HC, 1240 EV nanometers again. Oh, I had that 2 pi, so I have to put a 4 pi down here, 4 pi squared. I have my E naught, my 5.1110 to the 5th electron volts. And I have my 1.44 EV nanometers. Well, I don't have to go know the mass of the electron off some table. I don't have to go running around trying to convert between SI units. It's all been put into atomic units to make the calculation easy. All of these constants are known. They know that, they know that, they know that, they know this, they know this. Choose your N's, 1, 2, 3, 4, and you have your R's. There are no adjustable parameters. So you now have something that, based on this, predicts what the size of an atom is, with nothing to be adjusted. Plug that in for hydrogen, and the ground state, which is the lowest N, which is 1, and you'll get a number that looks like this. Now, that's the best way in many ways to write it, but a lot of us prefer to write in terms of 10 to the minus 10 meters, which is given the symbol, the angstrom. Rather than working in nanometers. And if you do that, this is 0.529 angstroms, half an angstrom. And that's the size of the hydrogen atom's ground state. That symbol is usually given a separate symbol. You see the A kind of looks like an angstrom, and the 0 kind of being initial or lowest. This is called the Bohr radius for the hydrogen atom, and it's a number you should know. I wouldn't expect you to know the extra decimal places, but I would expect you to know that it is half an angstrom. It sets the basic size of atoms. So all atoms are on the order of 10 to the minus 10 meters. All nuclei are on the order of 10 to the minus 15 meters. Wavelength of light is on the order of half a micron. There's certain basic sizes that you should have pictures in your mind when you're talking to people. All right? If you take this, for when Z is 1 and N is 1, that's that big constant over here, then you can replace doing all of these plug and chugging, and you can simply write it like this. For any single atom, the orbit of the nth orbit is n squared divided by the atomic number times half an angstrom. You can be asked to find any particular orbit for any particular 1 electron atom. It's an example of that. You can be given the following type of a question. What is the ground state radius for a beryllium 3+ atom? V is equal to 4, N is equal to 1, R to the N, in this case R to the 1, is equal to 1 squared over 4 times A naught. Plug in the value of A naught. It's a little bit more than 1/10 of an angstrom. All right, simple calculation. Make sure that you know you can apply that formula to a problem like this. I give you a lithium, I could give you a beryllium, I could give you a boron. I'll give you some sort of single atom, and I'll ask you to calculate the radius for it. Next thing that you can be asked, energy levels. Now you have this for R. You can actually, if you want, go back and put it into there. You also can replace the moment of inertia Now here's kind of a tricky thing. If we assume that the proton in the hydrogen atom is so much more massive than the electron, which it is, we can ignore the fact that as the electron goes around the proton, it's pulling on it just as much as the proton is pulling on the electron, the third law. So the idea that, we kind of think of this electron, there's the proton. The electron goes around and proton is stationary. That's not true. As this guy is pulling on that, it's pulling on this. So this guy's got to move too. He's got a force causing acceleration. Well, then you got two things moving. That makes life hard. There is a trick in physics to get around that called the reduced mass. To account for that, when you replace this I, you really shouldn't replace it with the mass of the electron times r squared. You should replace it with the reduced mass. And I talked about that in the thing. If the effect is small, yes. But spectroscopy was so good. They could measure such small wavelength shifts, they could see this effect. So Bohr knew about it, and certainly he did correctly. I'll ignore it for now and say that we're going to replace the moment of inertia just with the electron's mass times r squared, and I'm going to treat that proton like he doesn't move. So in my notes, if you work through them, you know that I just, again, sat down and started applying physics 1 and physics 2. I put this in for the moment of inertia of a point particle in physics 1. I used the fact that this was mv squared, twice the kinetic that we talked about for circular orbits. Plug that in up here. So he gets L m 2mr squared minus L mr squared minus L squared over 2mr. He's got the value of r, plugs his value of r in. So what does he get? A bunch more dang constants. There's the rest energy of the electron. There's this radius of the electron's orbit. Here's my hc, you don't get to change. Here's 2 pi, you don't get to change. Again, no adjustable parameters. They've all been measured before. So the only thing that you get to monkey with in the Bohr model was your original 4 assumptions, nothing else. And when you're done, you get a prediction of the energy levels that you compare to experiments. And what he finds is that Z is 1 and that N is 1. The value for the hydrogen atom is minus 13.6 electron volts. So he's got one of his levels. Then it says, okay, fine, put 2 in here. Well, if you put 2 in, you get your next level. Minus 13.6 eV over 4. Now, put n equal 3. Minus 13.6 EV over 9, and so on. And he can calculate these energy differences and the wavelengths that he would see. And he can compare them to spectral lines. And they match. So he explained spectral lines with 4 assumptions with no fitting parameters. He didn't come here and get a formula and adjust it until it matched the spectral lines. It just gave the spectral lines. So before he has a huge set of data, and some people have some formulas to fit that data, but they have no reason for why it works. Now you have a physical model that predicts the results of stuff. Now the Bohr model is wrong because it predicts lots of other things. It predicts angular momentum, and they're wrong. Furthermore, if I'm looking at this model, I would say it can make this jump, and it can make that jump, and it can make any jump up here. You know, I could have another one up here at 4, and it could go like this, or it could go like that, or it could go like that, and so forth. It doesn't say which one should be more likely. It doesn't say which one should be brighter. It doesn't tell me that some of them don't occur. These are facts that quantum mechanics explains. So the Bohr model does not explain a lot of stuff that modern quantum mechanics does. But what it does really good is gives nice little numbers that you can subtract to find the energies, and then you can use AC over lambda equal E, and you can find the wavelengths of anything you want. So it is incredibly useful for doing these type of energy calculations with a 4-function calculator. And that's why we keep it around. And it was useful for giving people a starting point for developing the correct physics in the same way Galileo's work was useful in giving us a starting point in Kepler's work. But it's not correct, because it also gives lots of wrong things. Now, if you take that hydrogen 13.6 and you put that in for all of this junk, you can write the energy formula for all the atoms like this. Assuming, of course, that we're considering only one electron atoms. Take the hydrogen ground state, minus 13.6, multiply by the atomic number squared, and divide by the n for your particular energy level, and you can give me the energy diagram for whatever single atom you want. So, same sort of type of problem that you could be asked. For beryllium plus 3, draw an energy diagram. Labeling the 3 lowest energy states and the free electron state. So again, we got Z equal 4. I've got a bunch of states. So this is the 1 state, the 2 state, the 3 state, the 4 state. That's they only asked me to do the 3 lowest. Okay. Somewhere up here, the n equal infinity state. That's when you get out of the well. So you've got a certain amount of energies. All these energies are going to be negative because you're in the well. If you get more than enough energy to escape the well and get a positive energy, then you leave. So if I can raise it more than from here to here, I will ionize the atom. To find these energies, Z1 is minus 13.6 eV. And then my little formula here is so useful to know. Multiply by Z squared, divide by N squared. Well, that means 16 over 1 squared. Punch calculator. I don't know if I've actually done a problem. Minus 217.6 electron volts. If you give an electron more than 217.6 electron volts, you will ionize this atom. So if you give it 220, let's say, then 217.6 is necessary to jump it to here. And the remaining couple of electron volts will be kinetic energy that the electron will have when it flies out of the atom. If you give it less, the question is how you gave it the energy. If you give it a photon, it must either totally absorb the photon if it's going to be bound, or nothing. That's your choice. To totally absorb the photon, the energy of the photon has to match the difference between the levels. If you shoot an electron at it, an electron can give it some of its energy and still have energy to go on out as a free electron. So an electron impact, you can ionize, you can excite, even though you don't match the energy levels. So another type of question that's often asked, and there's several in your book, he'll say, if a photon comes in with a particular energy, can you excite this particular electron? And the question is, does the energy of the photon match the difference between a couple of the levels? If the answer is yes, then you can excite it. If the answer is no, you cannot excite it. On the other hand, he'll ask the same question for an electron, or proton, or alpha. It doesn't have to match. It just has to be enough. So the minimum would be enough to get from here to here. I can calculate what that is. Z2 would be minus 13.6 electron volts times 16, or even easier, minus 217.6 divided by 4. Put that in and you come up that it's minus 54.4 electron volts. And if you go ahead and do the rest, you can find this is minus 24.2 electron volts. And this happens to be minus 13.6 electron volts. And that's 0. So it is relatively easy with the Bohr atom to fill out a table of energy levels. And with that table now done, you can ask questions like, how much energy is required to excite it to here? Huh?
You subtract 217 minus 54?
Yeah, you take 54.4 negative, and you subtract a minus 217.6, and you have the answer. And then if you want to know the wavelength, you just take 1240 and divide by that energy. And you've got the wavelength to be absorbed. So if you mastered the energy Einstein equation, and now you can get the energy levels to find the differences, you got everything you need to do a whole bunch of problems. Notice that when you go up this way, you become less negative. And so the difference is positive numbers. On the other hand, if you go here to here, you're going into a more negative number, so the change is negative. That's the change in the atom. Right? So if the atom is more negative, it loses energy. Where does the energy got to go? Out. There's a name for the out. It wiggles and it goes out the speed of light. What do we call those things? Photons. So you take the negative of the change in the energy of the atom, that's the energy of the photon that's emitted. And you again use 1240 divided by the energy and you can find the wavelength of the photon. Now there's one other notation that you need to know. These n's are the quantum numbers. They determine the eigenvalues, the energies. But people often like to say, hey, this is the ground floor, so this is the ground state. The lowest state you have. The ground state is the n equal 1 state. This is called the first excited state. But the first excited state's n is what? 2, not 1. This is the second excited. So sometimes the problem says it goes from the second excited to the first excited. Make sure you don't use n equal 2 to 1. It's 3 to 2 in calculating the energies. Okay? If you take something from here up, that difference is called the binding energy. If you go from the ground state to a free, it's called the ionization energy. All right, make sure you read through the rest of those notes and study Bohr well. We basically finished through chapter 4, and we will move on to chapter 5 next time.